In this video, we're going to start our exploration of some of the things that affect code quality. In particular, when we look at some code, how do we tell whether it's code of good quality or poor quality, and why does it even matter? One of the reasons why it matters is that software is never static. Once it's been written and proven to be useful, it's almost inevitable that somebody will want to make some changes, make some improvements, add new features to it. And so software typically goes through a process of extension, perhaps moving to other environments, different platforms. Bugs will appear and need to be fixed and corrected. And that process can last a very long time, not simply weeks or months, but possibly even years or decades. And over the course of its life, software is often worked on by very many different people, and often people that had nothing to do with its development in the original stages. And one of the reasons why quality matters is that good quality software is going to be more easily comprehensible by other people, it's going to be more easily changeable by other people, and ultimately is likely to lead to the software being able to be used for very long periods. So really there are only two options for software. Either it is successfully continually maintained, and the ability to do that relies a lot on the heritage, its roots of quality, or it's going to die. And software that can't be maintained is either going to have to be thrown away, or if an organization has come to rely on it so significantly, it's going to incur huge costs to keep running. So we want to look at some of the factors that affect code quality. We're going to carry out the exploration process by looking at a very simple game. It's essentially the beginnings of a game that we'd like to develop further. But before we do that, we want to reassure ourselves that we're starting from a position of good code quality. Because if we try to extend this and add new features to it, and we haven't started from a position of good code quality, then the job is going to get harder and harder and harder as we move along. So we want to observe the current state of the program, fix any issues that we see with respect to code quality, and then we'll be able to move forward with a lot more confidence that things are going to go more smoothly, because we're always starting from a position of good quality, and we will try to maintain that as we move along. The existing project has several classes, and we're going to start by investigating what all of these classes do. So we're not starting from the point of saying this is the new functionality that we're going to add and we're going to dive straight in. We want to try and understand what's already there, and as part of our exploration we're going to observe what we see and potentially identify issues that might need to be addressed. Now, the motivation behind this is that we've already got some commands in the game. We can make movements around the game, and we like to add the ability to move in different directions. So for instance, up and down instead of north, south, east and west, which are the current set of directions. And that sounds relatively straightforward. Surely it's going to be easy just to add a couple more directions to those that already exist. But if we're going to be doing that from a position where the existing quality is low, then we're simply going to compound any of the existing issues if we just go ahead and add the new features in. So we're going to review the code and see whether there might be existing potential issues. And as part of that process, we will actually engage in an act called refactoring. So at this stage, although we have in mind that we want to make changes, additions to the game in order to add extra functionality, the changes we're going to make will not be about adding that functionality. They will be about improving the existing quality of the functionality so that adding new functionality is going to become easier. And we'll start that refactoring process with the game class after we've explored what the other classes already do. So let's take a look at the project now. Here's the project. It consists of 5 classes. Before we actually look at the source code, let's play the game and get an external sense of what the game does in order to understand in a little bit more detail what we're seeing when we look at the source code. I'll create a game object. The game object has a single method, play, and then we get some introductory text. Welcome to the world of Zuul. Type help if you need help. Well, let's do that. See what sort of help is available. You're lost, you're alone, you wander around at the university, and the command words are go, quit, and help. And up here we saw in the introductory message that we're outside the main entrance of the university and exits are east, south, and west. So let's try typing go, and we get an error message which says go where. So maybe we have to type go and then a particular direction. Let's try go east. And now we're in a lecture theatre. So we started outside the main entrance of the university. Now we're in a lecture theatre. There's only one exit, which is to the west. So presumably that's going to take us back to where we were. There's nothing else that we can do apparently, so we'll go west. We've tried east. Let's try the south exit. Go south. We're now in a computing lab with exits north and east. And again, presumably north is the exit to take us back to where we were. So let's try going east. You're in the computing admin office with exits west. So at the moment it appears that the game is fairly limited in the functionality. We've got the ability to move between different rooms or locations within the game scenario. And this is one reason why we want to develop the game further. It's potentially promising. It's a text-based adventure game, but there aren't any of the standard features we might expect, like items found in rooms, the ability to pick things up. There don't appear to be any other players within the rooms that we might encounter when we go into them. So those are some of the things we might think about adding in terms of functionality once we've sorted out any quality issues that we might encounter through looking at the source code. To finish the game, it looks like we have to type quit. We'll type quit and we get a goodbye message. So now we're in a position to explore the source code among the various classes and see if we can relate that source code to the kind of gameplay that we've already seen. Let's start with the command words class. The class comment at the beginning nicely tells us that the class holds an enumeration of all the command words known to the game, and indeed when we look down here there's an array with go, quit and help, which is exactly the list of command words that we tried out and were informed about by the program. There's a constructor. Nothing to do because actually it has no instance state to be initialized. The only field is a static field, so that belongs to the class as a whole. And then there's a query method is command that takes a string, and essentially it's going to look up that string in the array of commands. And the way that it does that is it uses the static asList method of the java.util.arrays class. It passes the array into there, a list is returned, and then we asked whether that list contains the string. So a fairly concise way of determining whether a particular string exists within the array of strings. Of course, we could have written our own search task. We could have written a loop to iterate over the array, comparing each item with the string we were interested in. But why not use a utility class to help us do that and save ourselves a little bit of coding? That's one of the principles we've thought about, that using existing classes, existing functionality will often help us to code things more quickly, potentially more efficiently, not necessarily more efficiently, but it will be a time-saving device that we're making use of here. That's the command words class. Let's look at the parser class. The word parser typically means something to do with processing input, and that's exactly what's going on inside the parser class. So the parser has an instance of the command words class that we've just observed. It's got an instance of the scanner class, and the scanner is given the command line input to process. And then there's a get command method that prints a prompt to the user, reads the user's next input line, so it's line-based input we're dealing with within the program, and then the scanner takes the input line, and the scanner by default will break up any text that you give it using spaces as a separator between words. So this is a way of actually breaking up an input line, tokenizing it in order to identify the individual words on the input. So we ask the tokenizer for the first word. If the tokenizer says there's another word available, then we read that as well, but ignore the rest of the line. So our parser is prepared to take a user's input and identify a maximum of 2 words on the input line for processing. It then checks to see whether the first word is one of the known command words, so it's invoking the isCommand method of its command words object. If that returns true, it creates a new command object, and we'll look at what the command class does in a moment, passes the 2 words as parameters. Otherwise, it still creates a command object, but this time it's passing the value null into the constructor as a way of indicating to that constructor that the first word is not one that's recognized. So we can observe the effect of that when we look at the constructor of the command class in a moment. So the parser class is concerned with reading a user's input and breaking it up into its separate tokens or separate words. Here's the command class. As we might expect, the command class has 2 instance variables, both strings. Those are initialized from the 2 strings coming in, although we have to bear in mind that that first parameter might be null. We saw that is one of the possibilities provided by the parser. Those are set, and then we have accessor methods for those 2 strings, command word, get the second word, and then there's a query method here which corresponds to the fact that we might be passing null in as the command word. So this method here looks to see whether we've got a null value there for the command word, and if we have, then it's going to be returning true to indicate that this word is not known to the game. It's not recognized. And then there's a query method here, has second word, that looks to see whether the second word is null, because if it isn't null, then there's a second word on the input. Let's look now at the room class. So a room represents one location in the scenery of a game, and it's connected to other rooms via exits, and we've got north, east, south and west as being labels in some sense for the rooms. As we look at the fields of the room class, we notice 2 things that appear to be significant, and at least one of these might be significant for one of the quality issues that we wish to consider as part of this overall consideration of the quality of the project as a whole. We note that the instance variables are declared to be public, and this goes against the convention that we've tended to follow, which is that we want to enforce encapsulation on class definitions. In other words, we want to give the instances of a class control over the setting and the getting of the instance fields that each instance has. And it will be interesting to observe both why these fields have been made public. Is there something significant about the nature of the room class that means we have to do that? And also the effect on the overall structure of the program. Does making these fields public create issues in other parts of the program which ultimately might reduce the quality that we observe? So we're not going to do anything about the fact that these are public at the moment, because we need to gain an understanding of what significance that has within the context of the game. but it's not uncommon for people to use non-private designations for instance variables in the Java code that they write, and it's good to understand why that might be the case, whether that's simply that they can't be bothered to write accessor and mutator methods, or whether there's some significant reason why it's essential that those fields are not private and that encapsulation is not being imposed upon the definition of a class. So we note this as an issue that we'll want to look at in some point in our exploration of the quality of the code. The second point that we note is that this is class room and these are fields of type room, and that's quite unusual. We haven't seen anything like this before. Whenever we've defined a class, it's typically been in terms of other classes. So for instance, the clock display class was defined in terms of number display classes. The music organizer class was defined in terms of an array list class. We've never come across the case where one class has fields or parameters or local variables of its own type. So what we have here is an example of what we call a recursive definition. And recursive means something defined in terms of itself. So the room class has instances of itself within its fields. Now, whether that's related to the fact that these fields are public or not remains an open issue. We don't yet know. We haven't explored far enough within this class. But again, we note that that seems to be significant. Does it affect the overall quality of the design, or is it a necessary artifact of the way that this game is designed and implemented? So two features we're observing in the instance fields. One, we don't appear to have encapsulation, and two, the room class is a recursively defined class. Let's look at the constructor. Something unusual about the constructor is that we're not actually seeing these instance fields being initialized within the constructor. We're seeing the description instance field initialized via the parameter, but there's no initialization here, which means that whenever we create a room instance, all of these four fields will have a null value, which then raises the question, how do they get set? What causes references to other room objects to be set in each of these instance fields? How is that achieved? Is that a separate initialization phase that has to be gone through whenever we create a room? If so, which part of the program is going to be responsible for initializing these four fields? So the room class is raising a lot of questions for us, some to do with overall program design, others to do potentially with the quality of the program. And these will be things that we'll need to think about and address as we explore more deeply within the program. Here's a mutator method, and actually this answers the question for us as to how those instance variables that are rooms get initialized. Clearly there's going to be some call to the setExits method in which four room parameters are received, and the body of the method says if any of these is not null, then we want to set the respective instance variable to refer to the room object that's being passed in. So here's our initialization of those instance variables. We're seeing that a separate step is required. It's a separate step that's invoked externally. Some other part of the program seems to have created some other room objects and now passes them in to tell one of the rooms what it's connected to, which other rooms it's connected to. And then here's a standard accessor method for the description string that was set on construction of the room. So the room class is one that we're probably going to need to come back to at some point in our overall exploration of the quality of the game and an understanding of how it's been implemented. Finally, let's look at the game class. So this is the main class that initializes all of the others. It creates all the rooms, it creates the parser and starts the game. That's what the comment tells us at the beginning. And let's see how that's manifested in the constructor. We have two instance variables, a parser and a current room. We note that actually this instance variable is not directly initialized inside the constructor, but we do see that a parser object is created. And then looking at the create rooms method, we note that it's private, it's not meant to be invoked from outside the class, and here's where all of the setup and all of the initialization of the game is happening. So all of the individual rooms within the game are created, and then here's the point where the linkages between all of those rooms are set. So each room is created independently with no connections, and then the connections happen here with null values being passed in when there is no exit from one room in that particular direction. So we would need to understand the order of these parameters by looking at the source code of the setExits method to understand whether this is north, south, east, west, or north, east, south, west, and so on. So a little bit of care needed in order to check the initialization has been done correctly. And then the final part of this method does indeed initialize the final instance variable current room. It says that the starting point for the game is going to be outside the main entrance of the university, which is exactly what we observed when we ran the game. Here's the play method that we invoked. A welcome message was printed, and then we've got a fairly standard iteration with a Boolean variable controlling it. As long as that Boolean variable's value is false, we're going to get the next command from the user, process the command, and the process command method will return a Boolean value which will set finish to be true once the game is over. So presumably the process command method recognizes when quit has been typed and returns true in that case, but in all other cases is going to return false. Finally, a thank you message is printed at the end of the game. Here's the welcome message, a little bit of introductory text. The current room is accessed to obtain its description via the access method, and that's printed out to the user so that they know where they are. And then a list of all the potential exits from the current room are printed. Now this is a point at which we notice the significance of having those instance variables in the room class defined as being public rather than private. We see that the game instance is able to directly access each of those individual fields, and this is something that wouldn't normally be possible if those fields have been defined as being private. So here we're seeing the fact there's no encapsulation within the room class means that an instance of the game class is able to directly access those fields. Here it's reading those fields. There's nothing to stop it actually changing those fields if it wished to, if that proved to be necessary. So that's a consequence of having those instance variables as being public. So all the exits are printed, and that's the end of the print welcome method. Here's the process command method. We see it returns a Boolean value. There's a local variable that's going to be set where if the user wishes to quit. If the command is unknown, so there we see that if the user typed something that wasn't recognized, then we print out a message saying, I don't know what you mean, and return false. So we don't want to quit the game. So that's why false is being returned there. But then there's no further processing to be done because the command is not recognized. If the command is recognized, then the command word is retrieved, and there's a sequence of checks to see which particular command it was. Now, one of the things that we note is that we've got literal text here which directly relates to the text that the user has typed. And we saw a similar set of text in the command words class. So if we were to add new commands into the game, we'd need to add them both to the command words class, and we'd need to have a separate if statement here in order to recognize and check for and invoke the functionality of that command. Then if quit has been typed, then we process the commit quit command in some way, and again that returns a Boolean value as to whether the game really is going to be quit, sets the local variable, and that's the value that gets returned at the end. So it looks like there's some potential for the quit command to allow a user to cancel their desire to quit. We'll see whether that's the case when we look at the functionality of the quit method. Here's the print help method. Again, we note that all of the command words have been literally embedded within the text of this method. So if we introduce a new command, not only do we have to add it to the command words class, we also have to add it to the print help. We also have to add it to that sequence of if statements in order to recognize and act upon the command. So we're beginning to see some of the effects of making developments to the game, for instance the addition of new commands, and some of the places where we would have to make multiple changes in order to achieve that. Here's the functionality of the go command. We saw this when we ran the game. If we didn't say where it was we wanted to go, then we got the message go where, and nothing happened. If we type a direction, then the second word is retrieved, and then there's a sequence of checks to say which direction do we wish to go. Is it north? Is it east? Is it south? Is it west? And once again we see evidence of that lack of encapsulation in that we're directly accessing the instance variables of the current room object in order to find the room object that's the next room we're going to be going to. Now we recognize that any of these could well be null, so if there isn't an exit in a particular direction, that variable is going to be set to be null. And so we check down here, if next room has been set to null as a result of this sequence, then there is no door and there's no further action. Otherwise, we're now changing the current room instance variable to refer to the new room object that we're about to move to. And then we notice a sequence that we've actually seen before. So we saw this idea of printing out where we are and what the exits are when we looked at the method that was introducing us to the game. So we're seeing exactly the set of statements here. You are in this room description, and then here are the exits. Down here. So what we're seeing is what's called code duplication. We're seeing some code that's in two separate places. And if you recall, one of the things that we're contemplating doing is adding new directions, adding the ability to go up and go down, maybe up the stairs or down the stairs in a room to one above or one below. If we were to add those new directions, we're going to have to add them in two places. We're going to have to add checks for up exits and down exits in two places and the necessary text to go there. Now you might think that it really is no big deal to add extra code in two different places. We can type it in one place and then copy and paste it to the second place. However, this is something that we're really going to want to avoid. One of the main problems with code duplication is that it can often be difficult to know whether you've put the duplicate code in all of the places that it needs to go. In effect, you need a deep understanding and knowledge of the whole of a program in order to know all of the places that you need to go to in order to introduce multiple new code or make changes to existing code in all of the places where it's duplicated. And a much better approach is to locate the duplicate code in one place, typically in a dedicated method, and then invoke the method from all of the places that need that duplicate code to execute. And that's a process that we'll see shortly. So this is going to be our first improvement. We're going to eliminate the duplicate code that we see inside the game class once we've followed through on observing the rest of the game source code. Here's the quit method, and here's where we see that actually the quit method might cancel the quit. So if the user has typed a second word after the word quit, we're going to take that as an indication that they haven't quite understood what the quit command is meant to do, and return false to say, actually don't quit the game at this point. But if all they've typed is quit, then we're going to return true, and that will cause the game to end. In summary, for the game class, we've identified a couple of issues. We've identified the fact that there's a block of code that is duplicated in two places, and we've also identified that the lack of encapsulation in the room class is allowing the game class to directly access the values of the fields defined inside the room class. And this is a more significant issue than the code duplication issue. So that's something we're going to spend a bit of time looking at in more detail in a later video. But for the time being, let's address the fact that we've got this duplicate code here and earlier on, and let's eliminate the duplication so that it will ultimately be easier to introduce new directions and place code in just one place, and reduce the amount of effort and the potential for error in missing some place that it needs to be added. So let's define ourselves a new method, and we'll place it down the end. Because this is for internal refactoring of the game class, it's not additional functionality we want to add to the game as a whole, we're going to make the method private. And we're going to call it print location info. Let's put a call in here to make sure that we don't forget to obtain the functionality once we've moved the code. And then we're going to cut all of that text, place it inside the method. Let's indent that appropriately for the method. Let's add a method comment. Print details of where we currently are and what the exits are. And now we can use that call in the other location where we had the duplicate code. And completely delete all of this duplication that we saw. Let's compile, close. Let's make sure we haven't broken anything. So what we just engaged in is a process of what's called refactoring. So we've made some changes to the program, but we've made changes that haven't actually added new functionality. We've improved the quality of the code, hopefully, without actually going backwards or forwards in terms of the functionality that's been provided. So we see that the introductory message is printed, tells us where we are, tells us what the exits are. If we say go west, then again we find out where we now are. So we've made some improving changes to the game class, which means that when we do finally add additional exits into the game, then there's only one place that we're going to need to go in order to ensure that details of whether there are rooms in those directions will appear. We'll go to print location info, we'll add a couple of extra if statements, and then the two places that call this method will benefit from the fact that that code is located in one place. So to summarize, the first indicator of bad design that we've seen is that code duplication is one of those. It makes maintenance harder, and it can lead to the introduction of inconsistencies. So the failure to alter all of the places where duplicate code exists when either we add something or remove something or maybe fix an error. It's not uncommon to fix an error in one place and then be tripped over by what is effectively the same error when some other part of the program executes the code that still has the error in that wasn't patched. And code duplication can occur both at method level and at class level. So we've seen it at the method level here, where two methods had duplicate code and we fixed it by introducing a new method. But it's also possible to have duplication across classes as well. We can end up with classes that do very similar jobs to one another. And one of the things that we see when we introduce inheritance into an object-oriented language is that that provides us with a very effective mechanism to eliminate code duplication at the class level.